Hi, can you guys hear me?
The professor.
I'm so sorry. I'm under the weather. My voice is not that great, so that's the reason I didn't record the other session because it's really bad. I cannot talk really well, so probably I will post some of the instead of like recording. Probably I'm gonna upload some PDF with some question and the solution instead of just having the recording. Does it make sense? Thank you. Does anybody has any question?
I'm sorry, I didn't hear.
I'm so sorry. I told that I'm a little under the weather, so my voice is not a good voice for recording any videos or for our two classes that missing. So probably instead of recording, I'm gonna upload a PDF with some question and solution, like for the final exam. So you guys have some idea about how to solve some of the question and how is the solution for that. Does it make sense?
I see. Thank you so much.
You're welcome.
Get well soon. I'm sorry you're sick.
Thank you. Thanks. Yeah, unfortunately. So bear with me today. I know my voice is not a great voice for teaching, but bear with me because it's end of this semester. So I want to make sure that I teach all of the things need to be finished. So I upload the homework 3 actually. It's only 2 questions. So you guys see it on the canvas, am I right?
Yeah, we can see the homework, but like when is the due of that homework, professor?
Actually, I put it July 1st. You can check it out. I put it July 1st because I uploaded late. So I just postponed the. If you want to submit it, you can submit it until July 1st, 11 a.m. So just in case you realize that final exam was hard and you want to compensate, you can submit that one too.
Is it
Okay.
possible, is it possible for you to do the homework free, do like instead of 11 a.m., maybe like 9 p.m. or 11 p.m.?
I should because I need to just grade everything and report the like grades to university. I don't know. I should check it out. So,
Please
but
do
if
so.
if it's possible, so yeah, I will try my best to do that. So, do you think it makes a difference from 11 a.m. to 9 p.m.?
Yes.
That would make a huge difference for me, Professor, because it's the
Yeah.
day after the final and I want to focus on the final before.
True,
Oh.
indeed. Great
Okay.
point.
Okay, I will post for it. I will try to help. Okay, sure.
Thank you,
So there are 2
Professor.
questions. You're
Thank
welcome.
you.
So you're welcome. So there are 2 questions actually. You guys can work on it. So
Yeah, I saw them. They seemed interesting.
yeah, so yeah, you have time. It's not mandatory, but just
If you
educate.
don't feel great, you don't have to do lecture today. You might want to take care of yourself, you know?
Yeah, thank you so much. But I prefer, I prefer to teach as much as I can today. So we missed already 2 sessions. I will upload some like PDF for that for sure. But I don't want to be this class again. So, but I'm so sorry I could not submit anything because I need to record 4 hours. I think with my voice, it's not probably a good idea to record 4 hours. So I will submit some PDF tomorrow morning so you can look at it. So it's better probably for you guys because I'm gonna post not only instead of 4 hours of teaching, I'm gonna post the question and solution at the same time. You can see some of the question that's gonna be maybe similar to the final exam with their solution. So, but anyhow, you can reach out to me or TA if you have any question. Does it make sense?
How is the format going to be? Can it be typed for the sample problems and answers rather than written out, if that's possible?
What do you mean?
So you know how you usually write your lecture notes on your
Yeah,
tablet?
yeah. Oh yeah, for that 2 session, yeah, it's gonna be typed. Yeah.
Okay, perfect. Thank you
Yeah,
so much.
that's gonna be 2 PDF actually. That's gonna be 2 PDF of that tape, not written. So because I'm not gonna teach it in class, so it's gonna be typed already with solution
Cool.
in
Thanks.
latex format as whatever I posted. Like solution for final, for the midterm or quizzes. I'm posting the solution for midterm tonight too. So you can have access to that one, and the TA is gonna start grading that.
Sorry, Professor.
Yeah.
Is homework 3 counting to extra credit, or it's just a homework?
Yeah, it's optional. If you look at like when I posted, it written that it's optional. It means you're not forced to do it if you don't want to do it.
Okay,
Was
got
it
it. And when's the final again?
Final is this Friday. I will write an announcement for sure. This Friday from 5 to 7:15.
Got it.
15
Thank you.
minutes. Yeah, you're welcome. 15 minutes for like submitting. Just one thing, because it's a final exam, it's not midterm. Make sure you submit it through Canvas, not send an email. Figure it out, anything, I don't know, 1 day earlier. Submit it through Canvas, not through email. So because like it's a final exam, it's different than midterm. Does it make sense?
Yeah.
Thanks for asking. Yeah, I'm a little under the weather. I'm fine. So probably let's just start teaching. So and I will teach as much as I can today. So probably, but today and tomorrow is gonna be our last session. So it's Thursday. So what I'm gonna do, as I mentioned earlier, I'm gonna post problem and solution actually. So for final exam, I will mention a few things tomorrow too. So what's going to be the final exam, how is everything, and then that's gonna be it. And if you have any question, I see a few people reach out. So I just send an email to TA, CC him. So just if you have any question, but anyhow, if you have anything that we need to be taking care of, anything, let me know before the final exam. If you have any issue or anything, don't wait for the last minute. So that's it. Let's restart. We talk about the trees. So this is the rooted tree. You remember we talked about the trees that we are trying to solve the problem. We say, okay, that was one of the questions that we explained. Okay, if M, we want to find M, we say, okay, is M was greater than 3 or less than 3? And just we go down the line. So to find this one. Here we have a root. And then what we are gonna do, we are moving from the root. So, okay, this is the root. For example, we have 3 subcategories for this root. One subcategory for this one, or probably 2 for this, and this one has only 2. So for different problems. As I explained earlier, so we have depth. It's gonna be depth, which is gonna be this layer is gonna be 1. This is 0, this is gonna be 1, and this layer is gonna be 2, and the last layer is gonna be 3. So that's what we are saying. It's 3 arid tree. It means it's go to 3 layer. So one of the most important things about trees is depth. When we are talking about tree, we say, okay, it's the distance from root. It means the last point any time that you have. If, for example, this is the distance from root is 0, there is no distance, and this part is 1 distance, and this part has 2, 1 and 2, and the last one has 3. So that's the most important thing. There is another definition of the height of the tree. We said this is gonna be depth of deepest leaf. So what does that mean? So it means that if I go to this layer, which is gonna be the lowest down the point. So this is gonna be the distance from the root. That's gonna be the height of the tree, because this is gonna be the lowest, deepest part in the tree at the distance. So that's gonna be the height of the tree. You consider that one. But what we are gonna say, there is a definition. What is this definition? Tell us definition. It says that tree is a rooted tree in which each internal, which is gonna be non-leaf node has at most k children. What does that mean? So it's a rooted tree. It means they start from root, go all the way down, each any of this internal non-leaf. For example, this they are leaf. So this one, they are leaf because they're at the end, but non-leaf trees, none of this part, for example, they are non-leaf trees. It means internal non-leaf node has at most k children. It means the maximum that they have is k. So here, look at this one. So this is leaf. This one is a leaf too. But this is root. But the others is this one and this one and this one. They are not. They are internal non-leaf. And then look at the maximum number of the children. Here we have 1, 2, 3. And here we have only 2, and here we have 2. What is going to be the maximum? Is going to be 3. So we say this is the TR tree because it has only 3 actually. So it has a maximum of 3. So, but what you remember, we talk about binary tree. Sorry. So binary tree is when the case is equal to 2. It means at the max, you have only 2 roots. One of them is 0, one of them is 1. So let's go back to case 2. Complete. It says complete binary tree. It means at the max, k is equal to 2. It means that every decision, every internal node has only maximum of 2. So, but if the binary tree, when we say is it 1 or 0, let's consider this part. Is there root? We go here, we say, let's make it a little smaller actually. Here we are here, and we have 2 branches. And this one actually. So we say, okay, depths. Let's look at the depths of the tree. Here, the distance from root is 0. Here we have 1 distance from root, and then let's go back. So this is binary. It means the result of anything 0 is yes or no. So this is gonna be depths 2, and then we go 1 layer down, which is gonna be 3, 0 and 1, and here 2. So okay, this is gonna be 1. Yes or no, that's the other one. And then let's go back another layer. So this is gonna go this layer, and this layer has 1 or yes or no, yes or no. So we have this dot here from root is 1, 2, 3. So this has 3 nodes from the root, and then let's go to the nodes. So how many nodes we have? The number of nodes here. Here we have 2 depths, which is gonna be 1 node only because 2 power of 0 is 1. And then let's go to this one. 2 power of 1 is just gonna be 2. And here we have 2 power of 2 is gonna be 4. And the last one is 2 power of 3 is gonna be 8. It means for the node is 2 power of the depth. You can see here we have 2, here have 1, 2, 3, 4, and this one have 8. This is the complete binary tree. It means in each layer you respond to 2 questions, yes or no. So it means that you have the complete, it's complete because it has all of them 1 by 1. So that's the reason we say it's complete tree. So for complete binary tree, what we gonna do is that the number of nodes at depth d is gonna be 2 power of d. That's the definition. But if, for example, if the height, which is gonna be the distance from the deepest, which is here, the height is 3, the number of leaves, number of number of leaves is gonna be 2 power of h, because like here the depth, the height is 3, and the number of node at the leaves, which is gonna be these numbers, is gonna be 8, 2 power of h. So what I'm gonna say is, okay, let n is equal to number of leaves. So this is gonna be what? It's gonna be n is equal to 2 power of h. So if we know the number of leaves is n, so n is equal to 2 power of h. And what is gonna be gonna get? We say, okay, h is gonna be log of n. It means if I know how many leaves I have, I can say what is the h, what is gonna be the height of that tree. So that's the other way we can consider. So what we can do, if this is a complete, everything we display here, it's a complete binary tree. It means in each layer, everything is complete. For example, we have yes, no, yes, no, yes, no. We have 2 of them all the time. If I have this binary tree, for example, this is another binary tree, but it's not complete because, for example, in this layer, I have only 1 of them. I have probably yes, or I have only probably no. That's the thing. So that's the thing that we consider about this not complete binary thing. What I'm gonna explain. Another thing is about the theorem. So what is gonna say? If I let T be a binary tree, it doesn't mean it's complete with n leaves and height 8. Then what's going to happen? If it's not complete, you say h is greater than equal log of n ceiling. It means if I know if it's complete, h is gonna be log of n, but if it's not complete, probably it's gonna be greater than ceiling of log n. That's what we are gonna have. So that's really important because we can use it in the future if you have any problem that you solve with binary tree. But let's prove it. Why we do have this one? I know that it's gonna be equal. Why it's greater than, and why it's like a ceiling? Not okay. That's the thing. So let's go to the proof. So what we are gonna say, we say let LT and HT be 2 number. One of them is gonna be the number of leaves and height. So this first one show the number of leaves, and the second one show the height of what? It's gonna be the height of binary tree. Okay, binary tree T. Binary tree. Okay. Let's use induction on what? H is equal to this one. Because we know H is the height, it's gotta be height of T. First, let's prove this one based on induction. There's a base case. Let's do first base case. If H is equal to 0, then what's going to happen? Then we say T has 1 node because it has only, it means it has only root, 1 node, which is gonna be the root, which is a leaf. That's the thing. If I have this one, if I have this node is not only the root, it's also it's a leaf because there is nothing connected to it. So that's gonna be a leaf. So what's going to happen? You are starting case, okay. N is the number of leaf, which is gonna be LT is equal to 1. So what's going to happen? Let's prove it. So let's get H is greater than log N. What is this becomes if I put it? h is 0, we know that is 0, and then greater than what? Log of what is 0? It's gonna be 0 greater than 0, so which is true. So now we prove that one. We prove the first base case is working. Does anybody have any question? Okay, let's go back to other parts. So I know the base case. Let's keep going as okay. If it's the base case, how do I prove my induction? So let's go to the second part, actually. Part B, as I explained in the past. Let's what we do. Let's h is greater than 0. It means we have a height. It means we have some leaf and root. And assume for any binary tree T prime with what? So let's consider h. So and then we know that the height of T prime is gonna be h minus 1, for example. Because one of them, so if that's the case, we assume that one. So what is gonna be that h of T prime is greater than equal log of LT prime based on this assumption. So we assume this one, and what we show, we must show h of t is going to be greater than ceiling of log of LT. And what it's going to show us probably is going to say h is greater than log of n. So we assume that for the tree that has less, only one height less, because we consider that one for the induction too. We say, okay, if it's correct for k, it's going to be showing it's going to be correct for k plus 1. If it's correct for k minus 1, we are going to show it's correct for k. So that's the reason we consider it's true. We assume it's true for h minus 1, and then we're going to show it's true for h. So, but how do we do that? So is it clear up to that? Okay, let's keep going. Let's define what we are gonna try to do. Let's T prime be obtained from T, because T prime has one less height than T. By what? By deleting all leaves at depths h. Because why? We said the depth is gonna be h minus 1 for T prime. Let's do that. But how it's gonna happen? I have this tree. So what I did, actually I removed these leaves. I removed the leaves at the end of at the last height. So now what I'm gonna have now, you see T prime has less height. So the height of T prime is h minus 1, because I remove this leaf at the end. So that's gonna what happened. So that's the definition. Does it make sense? So let's now I do have that one. Let's try to define it. Say, okay, let's note LT is less than or equal to 2 LT prime. Why? Why that's the reason? Because at the end of the day, since each node in T has at most 2 children. What does that mean? I know T prime, I can at least have 2 children. So if I multiple everything in T prime with 2 children, it means I keep going, adding to 2 children. It's gonna be equal to T, or it's gonna be T is gonna be less than that, the number of the node. So LT is gonna be less than 2 LT prime, because at the most you can have only 2 children. So it's gonna be less than 2 multiplied by LT prime. What it's gonna give us at the end, that's what it's gonna give us. Therefore, thus then LT prime is gonna be greater than or equal to 1/2 LT. So that's what's going to happen. If I switch this definition, it's gonna be this one. So let's go about everything I prove it. We have H minus 1, which is gonna be H T prime. I know that. Then I just assume what I assume here. I say assume that HT prime is greater than log LT prime. So let's put that one. So this is gonna be greater than value of log LT prime. And what is that? This is, we need to write it by the induction hypothesis. And then what you need to do? Next step, you say, okay, this is gonna be happening. So what I can do, instead of T prime, you know the T prime is greater than LT. Let's put this one. So okay, this is gonna be log of LT over 2. That's the definition. And then let's put it together. Let's bring it out. So it's gonna be log of LT. And this is because this is a logarithmic in 2. It's gonna be this one minus 1. This is gonna be this definition. And let's keep going and bring everything out. So it's gonna be log of LT. And then I can bring this minus out. And then, you know, because we say LT is the number of nodes in the decision tree T, so it's gonna be the number is gonna be n, as we considered in the past. So log of n greater than minus 1. So it's gonna say H minus 1 greater than or equal log of n minus 1, which I remove minus 1 from 2 sides, so it's gonna be log of n. So as required, we proved it. Because we say, okay, it's considered we have only H minus 1, which is gonna be, we show it for K minus 1, and we prove it's correct for K. That's a proof that we did with the induction. Does it make sense? And does anybody have any question?
No, that makes sense.
Okay, so let's see. Probably we are gonna have our last probably I'm gonna give us the last quiz. Let's see.
Professor, I thought you said there was going to be 8 quizzes total.
We already have 8.
Yeah.
Yeah, I'm just thinking that's I don't know, maybe probably let's put it as an exercise for you guys, not as a quiz. So exercise is gonna be let T be square tree with n leaves and height h. It means when we say k tree, so it means the maximum of any leaf is going to be k. So then what's going to happen? This is not a binary tree. This is another k here. It's a binary 2 array tree. So this is going to be k1. So prove that for this one too, h is greater than equal. This is going to be log of n k. Either like the this is going to be the base of k because we have k instead of 2. The previous one was 2. So that's the way we should do that. This is another like exercise you guys can try and do it. So what is going to happen? Why we need this one? So why we talk about all of these problems? So I'm going to explain why, because we try to solve other problem. You remember, like sorting algorithm or doing another thing. So we need to do this one. We need to have a problem that we can convert them to the trees and then we solve them. Give me one moment. So, and then I will explain about how the problem works. Just give me 1 minute, so I will be back. So sorry, I need water. So let's keep going. Okay. You can hear me, am I right?
Yes.
Yes,
Okay.
Professor.
So let's see, why do we need these trees actually? So what we are gonna say, given a problem P, any problem, you see, for example, one of the problem was like like you can see the coin change or any problem or the one that I consider for the uh, homework, you see there is a problem. Consider all algorithm that solve P. So you remember we talk about like greedy algorithm, or we can use dynamic programming by doing a sequence of basic operations, each having at most k outcome. And then what we can call them, we can call these operations like props or ki props. What does that mean? Listen, consider that you solve a problem that you do some nice basic operation, like doing a like plus or just for loop or any at this one, but at the end having at most k outcome. It means that if you solve a problem, then there is only k outcomes you are gonna have based on each step that you are doing. For example, you remember so what's up the binary tree, like m is was we are trying to find m, like m is greater than 3, and then we go down like m greater than 2 or m greater than 5. We just go down one layer by layer. So you can see, for example, this one has 2 outcomes, for example, or this one has 1 outcome. So the maximum, our maximum having at most k outcome, this one has 2 outcome only. It means this problem is gonna be the k, the props is gonna be operation is gonna be 2. So that's the reason we need this kind of tree to solve that problem. Because at the end of the day, you remember, I explained for each problem, we are trying to see which problem has the better runtime. Based on this definition, and if the height of the tree, you can see, okay, what is the runtime of this tree, how we can solve this one. So what's going to happen? We say, okay, any algorithm of this type that have only k outcome can be represented by a k array tree, that which what's going to happen, each internal node, you remember the internal node is the one that is not the root, that is not the leaf. Internal node is a k array prop. It means has k outcome only with at most k children. So what's going to happen? We say each leaf is a word. But because the leaf is gonna be a return value that you are gonna get out of your problem, because this is gonna be the end. It is you're gonna solve that one, and then you're gonna find it. For example, one of the problems that you can solve with decision tree is like if the picture is a dog or not, so you can start with the picture. It's like, is there any different specific structure in this one? Yes or no? I go down, go down. At the end, the return value is going to be, for example, being a dog or being a cat. So that's one of the problems. That I will draw one problem here in 1 minute. Okay, let's see if I can find a really good one to write. So Okay, let's talk about the weather actually. Let's see. Okay, so for example, this is my question. This is my problem. So that's my problem is like, should I play golf or not? For example, you look at the outlook, look at the weather. There are two things. There are three options. So if it's sunny, so if it's cloudy, or if it's rainy. So there are three, for example, for this problem. If it's sunny, there are two things that if it's sunny, so let's consider this leaf actually like this actually is better probably. So let's 1, 2, 3, and then let's consider these leaves. So it means windy. So what's going to happen based on the weather? There's 3 layers. If it's sunny, there is 1. If it's cloudy, there is 1. And if it's not rainy, so it means I have a problem that at each layer, so it's like, okay, sequence of basic operation, which is the question, for example, each having at most case outward. At most, when I ask sunny, cloudy, or rainy, the outcome is going to be only 3. So what's going to happen? If it's cloudy, I don't need to check anything. So go, let's play. But if it's sunny, there's 2 things. How humid is it? So we consider 2 options. If it's greater than 75, or is it less than 75? It means, let's see, the humidity. If it's less than 75%, or is it greater than 75? So that's going to happen. This is say play, and it say not play. As you can see, what is this coming from? It shows that at most in this layer, I have only 2 children. As you see, I said each leaf, this one is going to be a verdict, return value. So the return value is play or not play. That's the thing. And if you go to windy, we just, okay, there are 2 options. If it's windy, true or false, if it's not windy. So if it's windy and it's like true, it's not play, because you already have like rainy, windy, that's play. But if it's rainy and it's false, it's not windy, you can play. So that's some of the things. For example, you see in each wording, you are gonna have a return value. So in the system, you have at most k. So here you have a 3 array 3. Because at most in one layer has 3 and the other has only 2. That's what's going to happen. That's the definition of how we do this. But that's one of the problems that we are going to solve with this. So that's the reason it is important. That's a really simple example to show why we need this type of definition and trees and everything. But let's go back and say let n be a size of an instance of problem. How many problem, for example, you have, how the possible outcome, and then we say let f of n, that function, be the number of possible output values. The number of possibility that number of output, number of leaves that you can get, return value that you can get, let f be that one. What is going to be? No, it's going to be f of n is less than L of t for sure, because this is going to be the leaf of the tree. F of n is going to be less because this is the possibility. Some of them is equal. So for example, here we have only number of possibilities, play or not play, but the number of leaves I have is 4. It's f of n is going to be less than L3. So we say where T represents the K array tree representing an algorithm. As you can see, this is like a binary search that we do this one. So probably here we just represent that, but by one of the algorithm represented by 3. So how does it work? We say each downward path that we have from root to a decreasing leaf represents a particular logical path from input to output verdict. What does that mean? Let's go back here. What of these start from this? Starting from down, what is go down after starting from root and going down to leaf. For example, whether a study human grade less than say the 75 play, that's gonna be one logic that you say, okay, whether it's study and we do the human it is less than 75. So our logic is gonna be this one. That's the way. This is one logic to solve the problem. So then based on the what we have by preceding exercise. H is greater than equal log of K L T as I explained above. So this is gonna be the ceiling of log K. And then this is gonna be greater than what? It's gonna be log K, and we define that LT is greater than F of L, which is the number of possible outputs. So it's gonna be greater than F of L. That's the result. That's what's going to happen. We are gonna have we have a tree, which is gonna be the logic log of K F of N. F of N is the number of maximum output that you can get. So what does that mean? That at the end is gonna show us what? It shows worst case number of props. It means no number of props that we are gonna get is greater than log K F of N. If you know how many output you have, the worst case number of the problems that you need to solve, the problems that you need to solve is gonna be greater than log K F of N. It shows you how you are gonna get, what is the worst case scenario. So for example, let's solve some problem together. Let me write it here so you guys can check it out. So for example, I wanna you guys do a guess. I have M between 1 and 6. And there's like a guess, what is that? What is the M that I chose between 1 and 6? And you want to see what worst case scenario, how many comparisons you need to do, not how many. So I say, okay, M is gonna start from 1 to all the way to 6. It has 6 items, so the size of the N. When N is gonna be the number of the leaves, because at the end you are gonna reach to 1 to 6 because that's the leaf, so it's gonna be 6 number. So we say, okay, the number of output I can get, F of N is equal to 6 because that's the number of output that I'm gonna get is gonna be number 1 to 6. So that's what's going to happen. That's worst case number of comparison and we need to satisfy. What is gonna be the number of comparison is gonna be greater than, because that's the problem that you're gonna solve. That's gonna be problem is gonna be greater than log of 6, which is gonna be equal to 3. You remember we said, okay, in the average, in worst case scenario, it's gonna be 3 based on the. You remember we solved with two different algorithms. One of them was 3.3, and one of them was is equal to 3. If this is the worst case scenario, it's gonna be 3 or greater than 3. That's the way you are gonna consider. That's the way. Or for example, if you get, for example, guess who m equal to 1 to n, and then you get, okay, what is the number n? Number of questions you need to ask. So that's the, for example, that's what you need to do. How, okay, let me write the question and you guys think about it. I'll get back to you a second. What is the result? So let's take another example. Guess, you want to guess the number, like for example, from 1 to n. And then the number of output is going to be n for sure. And then how many number of questions you need to ask? Like you go on a game. So how many number of questions you need to get asked to solve this problem, to find the output? In the worst case scenario, probably you can guess it in the first approach. The code is, for example, 25, and it's correct, but probably that's not the case. What is the worst number of questions you need to ask to find this number? Guess this number. Anybody?
Sorry, I'm not sure.
So because this is the way you just, and I'm talking about the problem, like the past. So you guess, for example, I want to find number from 1 to n. I asked you, okay, my number, I chose number from 1 to 100. Guess which one is it? How many number of question in worst case scenario I need to ask? You need to ask to find that number. What is that? Based on how I explain. So if you do 100, no, it's not the worst case scenario. Probably you can find it. Yeah, 100 is something, but there is one way to do that. It's like if I want to consider the maximum, like the n is the output, the number of questions you need to ask is greater than equal in worst case scenario with log of n. It means if probably you're in the worst case scenario. You're not that lucky. You need to ask 100 questions. So, but in worst case scenario, the number of questions probably should be greater than log of n. So you cannot do better than that. So because I explained about everything above, about 6 numbers, or only one here we have n numbers. So that's the way we can consider that. Does it make sense? For example, let's see. For example, say I have number and the number of output. I say, okay, I have a number. It's 1 million. So I say, okay, guess between from 0 to 1 million. So I chose a number. Guess which one is it? So it's like a number of question I can get. In the worst case scenario, the question I need to guess is gonna be greater than log of 1 million. It's 20. Probably by 20, if I'm lucky, at least I need to ask 20 questions to find it. I cannot do better than this. If it's 1 million, you should be so lucky to find the guess at the beginning. But in worst case scenario, you need 20. If you get 20, so you will find it. So everything other than greater than 20, you will find it. That's one of the ways that we say, okay, does it make sense? Why it's important? Does it make sense? Yes, no, it doesn't make sense. Can you guys still hear me?
Yeah, I understand better
Okay.
this time, sorry.
What?
Yes, I understand, sorry.
Okay. Just want to make sure you guys got it. So if you got it, I can move forward because nobody responds. I don't know if you guys can hear me. So theorem. So let's see. I explain all of these things because I want to get to the point why it's important. Any sorting algorithm that performs comparisons at its basic operation. You remember, for example, merge source consider, okay, is it this greater than that one or is it less than that one? This is basic operation. Must do in worst case, at least, this is the worst case that they can get, at least log of n factorial. That's what they need to do in the worst case scenario. Comparison on input array of lengths n. So it means that if I do have a any sorting algorithm, we talk about merge sort, quick sort, there are more actually. And then you see, I showed you batch sort and one in the exam. So it means any of these one that do operation like basic, like is it greater or less than this worst? In the worst case scenario, at least this is the number that they need. This is the number of comparison they need to do. Other than that, they cannot do better than this. That's the thing that we need to do. And I need to prove it why. And then if you find a sorting algorithm, that's the thing that you can say about sorting algorithm. Does it make sense? Okay, so let's see how we prove it, why it's the case. So a verdict, for example, the result, which is going to be the result of sorting algorithm for input array. When you sort at the end of the array, what you are going to get at the leaf of the tree is going to be whole. It's going to be you permute everything. You consider everything, the permutation of elements, because you consider all the elements from A1 all the way to AN. So if you vertex means gonna be last layer. In last layers, so you have n elements. So you have element from A1 to AN. So you compare permutation of all elements. So it means the number of like f of n is gonna be n factorial. What is that thing? It means you can start, for example, if I have n1 to n5 and n, this is one of them. It means start with A1, then A2 all the way to AN. That's the first one. Another permutation is A1, A3, A2, all the way to AN. So it's going to permute, so different. So it's going to be n that n factorial. So because if you consider the first one n times, so you can consider, let's see how it's worked. For example, let's take A1 all the way to AN. I can choose the first one to be A1 or A2, A3, any of these. It means that I have n selection I can choose from n. But anything after that, I have only n minus 1 collection. So because I cannot do that one, anything after this. So it's going to be n minus 1. And then for the next one, I have n minus 2. And then all the way go back. Because of this permutation, it means I have the output is going to be n factorial. That's a definition. That's the number of output I can get based on the input. So, and then what's going to happen each comparison, what we are gonna do, for example, I less than ij. So that's gonna be the first, okay, this is gonna be greater or equal or less than, has exactly two outcomes. Because any comparison that you do, this one is greater than this one, is gonna be true or false. Two comparison, then pass, for example, k is equal to 2. Thus, if I want to find the runtime for this problem, look at the number of comparison is going to be greater than log of k to n factorial, which is going to be, if it's find this one, this is going to be omega of n log n. So it's going to be asymptotically, that's what we taught in the past, asymptotically, the number of comparison that we need is going to be greater than omega n log n. So that's the reason we say, okay, in the worst case scenario, it's going to be at least n log n. This algorithm for sorting. That's one of the things you need to know. Does it make sense? Okay. So that's the definition of how number of comparisons do we need. Why do we go to trees? Because sometimes trees solve the problem easier than the others. So we use it, as you remember, I talk about lower bound, how many number of operations do we need? We talked about one of them, it was decision tree. We go through the tree one by one down the layers. So, and we go down, so we find that stuff. So, but there is some definition about the height, why it's gonna be happening. But the first thing we learned, so it's this is the one. Any sorting algorithm that comparison basic is gonna have this one, gonna have this log. You see, remember, I just defined this one here. So this is gonna be log and factorial. That's a definition that we have. Let's go to define a few things else. So let's see the definition. So then let's talk about the average height of a k-array tree. Tree is the average fresh leaf depth. The average height, for example, I have a tree, I know the height, but the average height of any tree in average, if it's ki, if I don't know what's going to happen based on the leaf. So I can have this one, I can get left leaf depth can be D1, D2, all the way to Dn, and the average height, because it's coming from the leaf, it's going to be summation of all of them in each layer divide by number of n. So that's going to be the definition of average height, because in each layer I have d1 to dn. In average, it's going to be the overall, which is really obvious. So because we just do the average because it's the name of, you're trying to find the average in all overall the tree. Does it make sense? Let's go back and talk about the average height of a K tree with L leaf satisfied. What is going to be satisfied? We said the average height of a K tree with N leaves satisfies A greater than log NK. That's a definition. So we say, okay, any average height tree with L, if satisfy this definition, it means that number is going to be greater than log over k, which L is going to be the number of leaves, that k is going to be the k at each layer of the tree. So that's one of the things you need to know. So there is one more theorem, so we need to talk about that one, and then let's see. There is another theorem, which is say for a problem P, if I have a problem P, any algorithm doing only k array props in each layer, it means the output of each layer is going to be k props. What's going to do? But do at least log of f of n k such props in average case. Then we say there n is prop size, f of n is a number of vertices. Number of vertices. What does that mean? If it's the number of output is gonna be n, it's gonna be f of n, and then n is gonna be the prop size in each layer. So if you solving a problem that at least have at each layer, the output is gonna be k. So at least you have log of f of n k such props to in any cases in solving the problem. In average cases, actually, this is average. In average, if you want to solve the problem, you need to have this number, log of f of n k. So that's the way we do it. There is n in prob, and this is going to be the number of vertices. That's the way that we do that one. Does it make sense? Anybody has any question up to that? Okay, if you don't have a question, let me summarize what I'm talking about right now today about adversary argument. I didn't talk about adversary argument, so I will talk about it tomorrow. So let me summarize the decision tree. Probably that's gonna be done for today. If you have any, let me finish that one, and then I think I cannot continue anymore. So let me finish that summary, and then we are gonna keep going tomorrow about the other part. Decision. Probably, and we need to talk tomorrow. I'm not feeling really well. So decision tree argument first determines k, which is gonna be max. So if you have summary decision tree argument, first of all, you need to find k. It's gonna be maximum number of, this is my maximum number of outcomes to each prop of the data. Determine chi, which is the max number of outcome to each prop of the data, because you need to find which was in each layer how many number of outputs you have. And then second is gonna be determine doesn't mean that. Determine f of n, the number of, we need to consider two things. First of all, we need to consider k, we need to find f of n, the number of vertices with the output out of the problem for sure. Output as a function of input size. So the number 3 is gonna be conclude, because now you know at each step what is the crave, what is the maximum output, and the next one is gonna be conclude any algorithm for P that does only props in one. So any algorithm that do props in one does at least, what is that? Based on the results, at least it needs to do log of f of n k prop in the worst case scenario. And because we explained this one, so okay, if this is k, it's gonna be k in each layer and output is gonna be f of n. In worst case scenario, you need this one props at average, and I talk about average too, at least log of f of n without the ceiling props for in the average case. You remember we talk about average, we talk about like average. So that's one of the things we need. I want to teach today. So we talk about decision tree. We are gonna talk about adversary arguments. The same guessing game that we have, for example, find from 1 to n, 2 players play, chose the number between 1 and n, ask question, one sequence of question. A cheat, and then A goals is to play the game as far as possible. So probably to know what is the solution. Each answer must be consistent with preceding answer. That's the way adversary argument works. So we are trying to do adversary one. So I will teach with this one tomorrow, which is coming from like you guess the game. There are 2 players, they're trying to find a sequence, but the one that knows the problem, it's the goal is to cheat, try to prolong the game as far as possible because he wants to takes more time. So that's the adversary argument. So I will teach adversary argument tomorrow actually. So anybody has any questions so far? I think I cannot continue. Probably it's better to just finish the class right now. I'm so sorry. I tried my best to just teach as much as I can.
I understand, Professor.
Hope you feel better, Professor.
Thank you so much. Thank you so much for understanding. Thank you, everyone. So I will post the PDF for this question and solution tomorrow, tonight or tomorrow morning for sure. I put this other solution for other quizzes, everything, and then we are gonna go through all of them tomorrow. So we talk about everything and get ready for the final exam. Thank you, everyone, and
Thanks so
have a
much.
great. You're welcome.
Okay.
Have a great.
Do we talk right now, Professor, or
Yeah, let's just, you want to talk in private?
do
let's
you in a breakout room, please?
Right, let's just give me for a few minutes. So
Okay.
the students is to, maybe they have a question. Give me a moment. Okay, does anybody have any other question? You're welcome. If you guys don't have any question, see you guys tomorrow for the last session, and then we have a final exam on Friday. Anybody has any questions so far? You're welcome. Let's see. There are like 6 people, 5. Anybody else has other than Andy has any question?